Hello students. So in this video we'll move on to the next module, that is Fourier representation of non-periodic signals. So here the representation of a non-periodic signal will be of two methods, that is we are transforming this in one domain to another domain, that is from time domain to frequency domain, or vice versa. We can do both if we take the inverse of that. Now here we are considering both continuous and non-continuous time signal and discrete time signal. So for continuous time signal, it is just a Fourier transformation or continuous time Fourier transform. For discrete time signals, it is discrete time Fourier transform. So we'll stick to this discrete time Fourier transform. Now here we'll be considering only discrete time signals. The short form of calling this discrete time Fourier transform is DTFT. Usually it will be represented or mentioned in this way only, DTFT as a short form. Now this discrete time Fourier transform of a non-periodic signal is given by x of n is equal to 1 by 2 pi 0 integral of 0 to 2 pi x of e power j omega into e power j omega n d omega, where this x of e power j omega is equal to summation n varying from minus infinity to plus infinity x of n e power minus j omega n here. So since it's a non-periodic signal, so we will stick to just the limit from 0 to 2 pi, okay, or the limit we can also alter this from instead of 0 to 2 pi, we can also take this from minus pi to plus pi, which is the most frequently used one, from minus pi to plus pi. So both will give you the same result no matter what. So most of the cases the limit will be from minus pi to plus pi, so we'll stick to that only. Now x of e power j omega is the summation of x of n e power minus j omega n. It is a non-periodic signal. Now what is this x of e power j omega? So this is nothing but the discrete time Fourier transform of a signal x of n, which is represented in frequency domain. So as in the previous case, here also the first equation, that is equation 1, is the synthesis equation, and equation 2 is the analysis equation. Okay. Now in this format also we have some properties. So the properties of DTFT. So we list the properties here first, and then we'll take one property at a time and we'll derive that with proof. Okay. So the first one is linearity. The second one, time shift. Frequency shift. Scaling. Frequency differentiation. And we have a summation, convolution, modulation, Parseval's theorem, and finally symmetry property. So these are the properties of discrete time Fourier transform. That is, we have 10 properties here. Let's take one by one here. So let's start with the first property, that is linearity. So what does the statement of this linearity says? So the linearity property, so the definition is given by like this: if x of n, so here we have to mention what we are performing. We are performing discrete time Fourier transform. We'll give x of e power j omega and y of n, y of e power j omega, then z of n is equal to a x of n plus b y of n. So here a and b are the scaling factor. We can use some other variables as well, or alphabets. So this is denoted by a x of e power j omega plus b y of e power j omega. So this is the definition of linearity. Now let's take the proof of it. So we have x of e power j omega is equal to summation n equals minus infinity to plus infinity e power minus j omega n. So let's call this as equation 1 here, and we have y of e power j omega is equal to summation n varying from minus infinity to plus infinity y of n e power minus j omega n. So similarly, z e power j omega is equal to z of n e power minus j omega n here. So let's substitute z value here. So z is a into x of n plus b into y of n e power minus j omega n. So let's put these two in the braces, in the bracket. Now if you multiply this, we'll get summation equals minus infinity to plus infinity a x of n e power minus j omega n plus b y of n e power minus j omega n. So this, so if you split this by taking this term outside, the variable, constant variable, so you can write it as a n is equal to minus infinity to plus infinity x of n e power minus j omega n plus b summation n is equal to minus infinity to plus infinity y of n e power minus j omega n. Now these two terms we have represented in equation 1 and equation 2, that is x of e power j omega and y of e power j omega. So this we replace with x of e power j omega and y of e power j omega. So we will end up with a into x of e power j omega plus b into y of e power j omega. So here we have z e power j omega. So this is the proof of linearity property. Okay. So next move to the next property, that is time shift. So what does time shift property says? So it says if x of n gives x of e power j omega, then y of n is equal to x of n minus n naught. So it should give us x of y of e power j omega is equal to e power minus j omega n naught into x of e power j omega. Okay. So let's start with the proof here. X of e power j omega is equal to summation n equals minus infinity to plus infinity x of e power minus j omega n. So we call this as 1 here. Similarly, y of e power j omega is equal to n equals minus infinity to plus infinity y of n e power minus j omega n. Now what is y of n? So let's substitute y of n here. So n equals minus infinity to plus infinity. So y of n is x of n minus n naught. So that we substitute here x of n minus n naught e power minus j omega n. Now we replace this n minus n naught with some other variable. Put m is equal to n minus n naught. So this implies n is equal to m plus n naught. We have to replace this n here with the respective variable. So if that happens, and here the limit n will be n will changes from m here because we have m plus n naught. So that's why. Moving on, y of e power j omega is equal to summation m is equal to minus infinity to plus infinity x of m e power minus j omega m plus n naught. So if we go for further simplification, so let's multiply this omega m and e power minus j omega n naught. Now this term will be the constant with respect to the summation here because we are m varying from minus infinity to plus infinity. So e power minus j omega n naught summation m is equal to minus infinity to plus infinity x of n e power minus j omega m. Okay. Now this term here is nothing but our Fourier transform definition. So e power minus j omega n naught, or you can see the equation 1 that we are represented. So based on that we can write this as e power minus j omega n naught into x of e power j omega. So here we have y of e power j omega. So this is the proof for time shifting property. Okay, so this term we are replace this here. So let's move to the next one. Okay, so frequency shift property. So the statement of this goes like this: if x of n gives you x of e power j omega, then y of n is equal to e power j beta n. So this is beta n into x of n. So if you perform transformation of this, then y of e power j omega is equal to x of e power j omega minus beta. So this is the statement of frequency shift property. Let's see what happens here. That means the shifting operations is performed in frequency domain. So that is the meaning of the property here. Let's take the proof of it. So we have x of e power j omega is equal to summation x of n e power minus j omega n. So we call this as equation 1 here. Y of e power j omega is equal to n is equal to minus infinity to plus infinity. We have y of n e power minus j omega n here. Now if you substitute this, y of n, that is e to the power of j beta n into x of n e power minus j omega n. Now we have the common base here, so we can combine these two. So if you combine them, you'll get, so let x of n first, e to the power of minus j, so we'll get omega minus beta into n here. So now if you observe this equation here, or you can compare this with the equation 1 here. Okay, so I'll just write the equation 1 once again here, that is x of e power j omega is equal to n equals minus infinity to plus infinity x of n e power j omega n. Now it says x of e power j omega, we have e power j omega n because we have x of e power j omega here. Now if you compare this, we have same term x of n, same summation. In place of omega, we have omega minus beta here. That means we can write this as a shifted version here in frequency domain. That means the omega can be replaced by omega minus n. Comparing this, we have omega minus beta here, we have omega here. So that's why this is nothing but x of e power j. In place of omega, we have to replace this term. So that will be the justification for this expression. So now based on this, what we can do, so you can write y of e power j omega is equal to x of e power j omega minus beta. So this is the proof for frequency shift here. Okay. So the next property is scaling here. So frequency shift is just nothing but we are the shifting happens only in frequency domain. Okay. So that is the meaning of this. So let's come to the scaling here. Now when you consider the scaling of a discrete time signal, so what exactly happens when a discrete time signal is considered? Uh, if you perform scaling operation, so some of the signal is discarded. That means in case of discrete time signal, when it is scaled, some signal is discarded. So we lose some samples in the signal. So that means we can't usually compare this with the original signal. That means we can't get the, if you perform the DTFT of the scaled signal of x of n, so it is not actually we are performing the DTFT of the original signal. Okay, that means if you perform x of n, you will get x of e power j omega. So fine, but this won't be the same if you perform this with a scaled version of discrete time signal, because some samples will be lost. So that's why, since it is a non-periodic sequence we are considering, so before going to the proof, or you can consider like this, we have to consider this thing, we call non-periodic sequence. So we consider a non-periodic sequence x of n. So I'll write it down. Consider a non-periodic sequence. So this x of n will be 0, where it is 0, unless the ratio n by p is integer where p is greater than 1. So this ratio n by p, if this ends up as an integer, then x of n is 0, where p value will be greater than 1 here. So what happens to this? Then if this condition is satisfied, then we have z of n is equal to x of p n, which is also a non-periodic signal. That means we are considering a periodic sequence with this condition. That means x of n will be 0 if the ratio n by p is the scale factor here. So, n by p, if this ends up as an integer, because the discrete time signal is present only at discrete instant of time, and these discrete values should be an integer value. So, if the ratio n by p, if you perform scaling, this is what happens in the scaling operation, the two time scaling. So, if this ratio ends up as an integer, then the x of n at that point is 0. So, this, if this condition is satisfied, then the signal z of n, which is the scaled version of x of n, is also a non-periodic signal. So, considering all these facts, so let us go to the statement of that. If x of n gives x of e power j omega, then z of n is equal to, you can take x of pn or x of an, any alphabet you want. Okay. Z of e power j omega is equal to x of e power j omega by p. That means this omega by p, what we have considered here, is the, it happens in this frequency domain as well. So, this is what the scaled operation or scale signal will look like. So, let us take the proof of this. So, we have x of e power j omega is equal to summation. So, why we are always defining this means this is just for the reference e power minus j omega n. So, call this as 1. So, z of e power j omega is equal to summation n varying from minus infinity to plus infinity e power minus j omega n. Okay. No need to call this as equation 2 here. Now, substitute z of n here, n is equal to minus infinity plus infinity. What is z of n? Z of n is x of pn e power minus j omega n here. Now, this term p into n, this portion, I will replace this with some other variable. So, put pn is equal to m. So, if pn is equal to m, we have n here. So, n is equal to what? M by p. M by p here. So, let us do this. So, when what happens? Z of e power j omega is equal to summation x of n e power minus j omega m by p. Now, I will just rearrange this for my convenience. N is equal to minus infinity to plus infinity x of n e power minus j. So, I will let omega by p here into m. So, here I think I should have replaced this with m here, x of m, and here also m. Okay. Now, compare this, comparing with equation 1. So, I will just write this equation 1 here just for the reference. N is equal to minus infinity to plus infinity x of n e power minus j omega n. This is x of e power j omega. Now, if you compare these two, we have the same limit in the summation, same variable here, the same thing here. Now, in place of omega, we have omega by p here. So, that means here also we replace that with omega by p. So, let us see what happens then. That's why when comparing this with equation 1, so we can write this entire term as e power j omega by p. Here z e power j omega. Now this is the proof for the scaling operation we are supposed to show. So that is what we get here. So if the scaled version of the signal is performed DTFT, that is transformed from time domain to frequency domain, then we will get the signal x of e power j omega is equal to x of e power j omega by p here. So I take one more in this video only, and in the next we'll take the remaining 5 here. So the next one is frequency differentiation. So the name itself indicates the differentiation operation will be in the frequency domain of the signal. Okay. So if x of n gives you x of e power j omega, then minus jn x of n. So this gives d by d omega x of e power j omega. That means the signal in the frequency domain will be the differentiation will be performed for the signal in frequency domain or vice versa. If we have a signal like this minus j n into x of n, if this signal is transformed, so then in the frequency domain we have to perform differentiation operation. So let's take the proof of this. So x of e power j omega is equal to summation n equals minus infinity to plus infinity x of n e power minus j omega n here. Now if you differentiate with respect to omega on both sides. Now if you differentiate this with respect to omega on both sides, so what do we get? We'll get d by d omega x of e power j omega is equal to d by d omega summation n is equal to minus infinity to plus infinity x of n e power minus j omega n. So now we interchange this differentiation and the summation here. That means we change the order here. So changing the order of differentiation and summation. So what do we get? We get d by d omega x of e power j omega is equal to so I'll first write the summation here, n equals minus infinity to plus infinity x of n. So d by d omega e power minus j omega n here. Okay. So now here if we perform differentiation for this term with respect to omega, so what do we get? So we get n equals minus infinity to plus infinity x of n. So we have e power minus j omega n. So that means minus j n into e power minus j omega n. So this is the differentiation of this. So that gives us n is equal to summation n is equal to minus infinity to plus infinity x of n, or I just write this down, minus j n into x of n e power minus j omega n. So here d by d omega x of e power j omega. Now in this part, so we compare with equation 1, comma, we get, so I'll write the equation 1 here, x of e power j omega is equal to summation n equals minus infinity to plus infinity x of n e power minus j omega n. Now we have to think this in a reverse manner. See here we have x of e power j omega which leads us with this signal x of n e power minus j omega n. Now, if you perform transformation of x of n, you will get x of e power j omega. So, this signal. If you perform transformation of this signal, that is minus j n x of n, then we will get the differentiated version of the signal in time frequency domain. That means x of e power j omega will be the differentiated signal. Okay, so that is what the differentiation property says that. So, based on this, we can write like minus jn x of n. Now, if you perform the transformation for this signal, then you will get a differentiation signal in frequency domain. So, that is the meaning of this. Okay. So, based on this comparison with equation 1, we can write it like this. Okay. So, this is the proof for frequency differentiation. So, in the next video, we will take the remaining properties and their proofs as well. Hope you have understood these methods here. So, if you have any queries, do comment on this video or you can reply to me. So, thank you for your time.